Hello, we're going to talk about dimensioning today. Okay, I'm going to talk about rules and practices and what we should do with dimensioning. Okay, an accurate dimensioning was most important demanding undertaking when designing parts. We'll look at a checklist to ensure that we followed the basic dimensioning rules. It's important to keep in mind that we can break some of the rules that we have. The important part is that the drawing is understandable to other people, especially the people making the part. Okay, should we dimension an object using dimensions that we use to draw the object? No, we should not. Okay, when we draw on a piece of paper an object or a part, it can be completely different than how it is manufactured. Okay, when we dimension, we need to follow acceptable standards. Okay, the standards that we use is ASME Y14.5 standards. There are a whole bunch of standards in order for drawing to be dimensioned so that all people can understand them. We follow standards that every company in the world must follow. Okay, and we have different organizations like ANSI, ISO, DIN, JIS, MIL, DOD, and CEN. Okay, Standards Institution. What we're going to look at mainly are ANSI standards, the American National Standards Institute. This institute creates the engineering standards for North America, which is where we live. ISO is the International Organization for Standardization. This is a worldwide organization that creates engineering standards with approximately 100 participating countries. Okay. When we talk about dimensions, they are comprised of 4 different parts. One, we have the dimension text, that is the distance that it's going to be. We have dimension lines. Dimension lines are right here. We have arrowheads, we have extension lines. We'll talk about each one of those extension lines. Okay, they extend from the view to indicate the edges referenced and hold the dimension line. Okay, so we have an extension line. We're going to take dimension from this end to that end. So we extend that up and then we put the dimension between them. Okay, we continue about 1/8 of an inch past the dimension line, and we have about a 1/16 inch gap here so that we can tell the difference between the extension line and the object line. Okay, dimension lines, okay, they can be horizontal, can be vertical, or they can be aligned, okay, like this one here. When stacked, they're about 0.4 from the view and about 1/4 of an inch apart. We'll just eyeball those. Okay, we won't worry about exact numbers there. Arrowheads are typical dimension line terminators, but there are other ones. Okay, so we can use the arrows. Here's an example of arrows pointing to the extension line that we're using. We can also use dots. Okay, or we can use what is called ticks. Can also use right here this triangle, and that represents a datum. Okay, we're going to be using mainly arrowheads. Dimension text. If dimension text will not fit between the extension line, it can be placed outside of them, like here. Okay, dimension text is placed in the middle of the line, both horizontally and vertically. Okay, leader lines. Avoid crossing leaders. Avoid having long leaders. Leaders that are parallel to adjacent dimension, extension, or section lines. Okay, careful of small angles between the leader and the terminating surface. We talk about dimensioning methods. There are 2 that are used. There is the unidirectional method, which means all dimensions are read in the same direction. Then there is the align method, which means dimensions are read in alignment with the dimension lines or side of the part. Some read horizontally, others read vertically. It's an example of both. Here is unidirectional. Everything is this way, okay? Dimensions are placed so they can be read from the bottom of the drawing sheet. This is commonly used in mechanical drafting, and this is what we are going to be using for all our drawings. Align dimensions are placed so that the horizontal dimensions can be read from the bottom and the vertical can be read from the right side of the sheet. Okay. Normally you'll see this type of dimensioning in architectural and structural drafting. Again, we are using unidirectional. There are two classifications of dimensions that we'll talk about, and that is size and location. Size dimensions are placed in direct relationship to a feature to identify the specific size. Location dimensions are used to identify the relationship of a feature to another feature within an object. Okay, so if we look at a part like this, we have a piece. Okay, it's got some holes in it. Okay, for example, the distance from this edge to the center line of the hole, that is a location dimension. Okay, from this edge to this hole is a location. From this edge to this edge, though, is a size. Okay, the width here, that is a size. From this edge to the center of here is a location. Okay, this is a counterbore, that is a size. This is a radius, that is also a size. We usually start off when we do the locations first, okay, and then the sizes second. Okay, dimensioning checklist. Each dimension should be clearly written with only one way to be interpreted. You do not want anyone trying to make decisions about what is what. A feature should only be dimensioned once. We do not want duplicate dimensions. Dimension and extension lines should not cross. Every feature must be dimensioned. Dimensioned features or surfaces should be done to a logical reference point. We're going to call those datums. You dimension circles. They should have diameters. An arc should have a radius. So if it's a complete circle, it is dimensioned as a diameter. If it is part of a circle, it is a radius. Center line should be extended and used as an extension line. Any circular feature must have a center line, even if that center line is not being dimensioned to in that particular view. Dimension features on a view should clearly show its true shape. Okay, we're going to have options where we can put a dimension at one place or another. We want to make sure that it clearly shows the shape. Enough space should be provided to avoid crowding and misinterpretation. Extension lines and object lines should not overlap. Dimensions should be placed outside of the part unless you really can't help it. Center lines or marks should be used on all circles and holes. Lettering should be legible, easy to read, and uniform throughout the drawing. They should be all uppercase letters. The minimum lettering height is about 1/8 of an inch, or 3 millimeters if we're doing a metric drawing. Dimension from feature to feature is known as chain dimensioning. It's commonly used and easy to lay out. It does have possible consequences in the manufacturing of the part, okay, because we have tolerances and they can accumulate, making the end product larger or smaller than expected. Okay, here's an example of a chain dimension. Now the problem is we have 3 dimensions here, and it's a 1/2 inch from here to here, 1/2 inch from here to here, 1/2 inch from here to here. Well, each one of those have a tolerance on them. Okay, so if we just dimension these 3 parts, okay, and they're plus or minus 10,000, so this could be 60, 60, 60. That may be larger than we wanted on the overall. So basically what we normally do is we get rid of one of these dimensions and we put the chain dimension and then an overall. Okay, it's like we show here. That way we have 1.5 up here with a tolerance of 10 thousandths. So our overall only has, even though it's 1.5, it can only vary by 10 thousandths instead of this way we had 30 thousandths. Linear dimensioning. The accuracy of the final product is determined by the dimensions on the drawing. If all dimensions originate from a common corner of the part, the object will be more accurate. This is called datum dimensioning. Datums ensure the tolerance or errors in manufacturing do not accumulate. Okay, so we use this as a datum point, which means that we take all our dimensions from that surface. Okay, so now we have 0.5 here, 1 inch here, 1.5 here. That stops our accumulation of tolerances. Here we have a datum down here, okay, in a dimension 0.25, 0.5, 0.75. Okay, this is the datum right here and right here. Whoops. Dimensioning symbols. Dimensioning symbols are used to replace text. The goal of using dimensioning symbols is to eliminate the need for language translation. Okay, just because we read and write English doesn't mean that everyone in the world and the people producing it may not read English, so we use symbols whenever we can. Here are some of the common ones. You've all seen a degree symbol. The parentheses here means it's a reference dimension. Here is a diameter symbol. We don't write DIA or diameter. Here is a radius symbol, an R. Okay, even though that's English. Okay, this shape here is a counterbore or a spot face. A V here is a countersink. Right here is the depth. Okay, little arrow here. X means places or by. So I might have 2 space X space 0.25. Means it's 0.25 in 2 places. Plus or minus symbol, center line, not used as much anymore. This is a square shape. This is an arc. This is a slope. Angled surfaces may be dimensioned using a coordinate method to specify the 2 location distances of the angle. Aligned surfaces may also be dimensioned using the angular method by specifying 1 location distance and an angle. So here's a coordinate distance or method where we dimension from here to here, dimension from here to here, and then an overall on both, and the angle comes out to what it is. Or we can point to one of those distances and then put an angle there. Okay, a full circular object again should be dimensioned using its diameters. Hole should use hole notes. Okay, so here we have a hole diameter. We need the diameter symbol. Here this is a partial circle that uses the radius. Okay, right here this tells us that this is a 0.5 diameter hole and the depth of that is 1 inch. Cylindrical parts may show their diameters in this manner. Dimensioning on the right side view could be too crowded. Note that the diameter symbol is used so it's not confused with the linear dimension. Okay, we should always dimension cylindrical parts in their rectangular view, and then we use the diameter symbol to indicate that it is a circular object. Chamfers. Okay, we can either put the angle and then the distance, or we can put 2 distances, or we can put 1 distance and the angle. Okay, normally if it is a 45, we may put just the distance and say it's a chamfer. Okay, we have external chamfers here, and then we have internal chamfers. Usually the internal chamfer is dimensioned to the outside dimension and then the angle. Fillets and rounds. Fillets and rounds on most CAD systems are exactly the same. A fillet is an inside radius. A round is an outside radius. Okay, in CAD though we call everything a fillet. When we're using a small one, we don't use a center mark. Okay, so here we have a small radius and a small radius, and we just put an arrow with the R there. If we have a large arc, then we may indicate the center of that radius. Dimensioning slots. Slots are normally dimensioned from center to center. And then we can either put the overall here, and if we put that overall dimension, notice we just put 2R, okay, which means there are 2 radiuses. Okay. Or we could specify that radius and leave that dimension off, or used less often, we can do from end to end and end to end. Okay, but the normal way of dimensioning slots is to the centers because that's how they're created. Okay, you have a mill or a drill and you locate the center of those. Okay, dimensioning radial patterns, we usually have a circle right here. Notice it is a center line. That is called a bolt circle. All the circles lie on that diameter. Okay, then we specify an angle. Okay, or multiple angles depending on what we're doing. Hole dimensions. Holes are specified using numbers and symbols. Okay, right here, this is a through hole. Hole drilled completely through this. Okay, the diameter is 0.38. Now they're showing the leading zero here. We don't show leading zeros either. Okay, so that's a through. This one is a blind hole. Okay, it's 0.38 diameter and its depth is 0.5. Here we show this symbol here. That is a counterbore. Okay, we point to the largest circle. Okay, the first one is the diameter of the hole. That is the smaller one. Then the depth of that. The next one tells us the outside. That is a counterbore. Here's the diameter and the depth of that. Okay, again, here is a counterbore. Okay, so we start off and we have a diameter symbol and then the drill diameter, which is the smaller one, even though we're pointing to the larger one. Then the counterbore symbol, diameter symbol. This one in this case is 20, and then the depth of 15. So the distance from here to here is 15. Okay, a spot face is nothing more than a counterbore, but in this case it may be on something like this where we have a curved surface. So we can't put the depth here because there's no surface to go against. So what we do is we put a depth or a distance from here to here. Okay, it is still specified as a counterbore. Countersinks go like this. They're on angle. Okay, again, we point to the outside, the biggest hole. Okay, put the diameter, then the drill size, which is a small hole. Here is the depth of that from here to here. Okay, then we tell it that it is an angle. Okay, and actually this depth is from here to here. Okay, and we tell it that this is a countersink. The diameter is 20, that is the outside diameter, and then the angle of the countersink. Here this will be 90 degrees here. You're going to see either 90 or 82 degrees. Okay, again, this is a hole diameters, and this is what we went over before. Okay, same thing here. There's a hole diameter. It's 0.38 diameter, and it's a 1/2 inch, 0.5 deep. This is a through hole because it says through. Okay, a thread note. Threads are dimensioned with the use of local notes. Discuss 2 methods. We have the ISO and the UNC, the Unified National Thread. Here is a UNC. We point again to the, not again, but we point to the smaller hole this time. Okay, and then we put like 5/16-18 UNC, or we point to here and you'll see it's an M12-1.56H through. Okay, when we look at this diameter, this is a UNC, Unified National Thread. The first one here is the major diameter, okay, which is the dotted line. Okay, -18 is threads per inch. 1 over the threads per inch is the pitch. We'll go over that in a different separate video. UNC stands for Unified National, and then we either have coarse or fine or even extra fine, and that's the distances between the threads. Okay, an ISO note. Put M stands for metric. Okay, this is the size of that nominal diameter in millimeters. Here we put 1.5. This is the threads, the pitch of the threads. Instead of putting the threads per inch, this is the pitch. Okay, then we have a grade. Okay, and again, these grades are for tolerances, and we'll go over those later. Okay, you may put right-handed RH or left-handed. Usually if it's right-handed, we don't put anything. If it's a left-handed thread, we put LH. Okay, and we can put through, or we can put the depth symbol and then a depth. Okay, dimension guidelines. Dimensions should not be duplicated or the same information given in two different ways. Okay, so here we have this is incorrect. Notice that we have 2-inch dimension from here to here. We also have the 2-inch dimension from here to here. Okay, it's better for these three dimensions. So we have 2 inches, 1.5, and 7.5. Okay, we can put them on this view, but they are better shown over here because it shows the profile of the part. Okay, here it's hard to see what we're looking at. Okay, same with here. We have a 1/2 inch and 1 inch. Okay, so we have a 1/2 inch here and a 1 inch here. This shows the shape better. And then we have the width here is 1 and the width here is 1. So we have all these duplicate dimensions, so we do not do those. Okay, and you'll see that the drawing becomes less crowded and looks much nicer. Okay, no unnecessary dimensions should be used, only those needed to produce and inspect the parts. Okay, again, like I showed before, you would not put 0.75, 0.75, and 0.5 and then an overall dimension. Okay, we would leave this dimension out. Okay, same here, we don't put 0.5, 0.5, and then 1. Okay, we would leave this one out. Okay, so this is how we would do that. Dimensions should be attached to the view that best shows the contours, just like we showed before. Okay, this tells us what we need to know, but it's very difficult looking at this view to see what we're looking at. I mean, this is an easy one to figure out, but if we have a complicated part, that could be a problem. So it's much better to dimension it this way. Whenever possible, avoid dimensioning the hidden lines and features, and that's not correct, so never dimension two hidden lines. Okay, like here, do not dimension the hidden lines. There's no reason to dimension hidden lines. Okay, we would dimension it over here. Avoid dimensioning over or through an object, so we would not put the dimensions inside the object here. Again, unless absolutely necessary, we would not put them there. We would put them outside the object like this. Always start with the smaller one and go up so that they don't cross each other. Whenever possible, locate dimensions between adjacent views. Okay, so here we have dimensions down the bottom, dimensions over here on the left. Okay, we don't want those there. Now this one here to 0.75. We will put that there because it would be more confusing to put a line out this way. Okay, but we want the dimensions between the objects if at all possible. Avoid crossing extension lines, but do not break them when they do cross. Okay, so here these extension lines all cross each other. That's okay. We're stuck with that. We can't do anything. Do not break those. Okay, the CAD even has a way that it will automatically break those for us, but we don't want to break those. Okay, if we don't break them, it becomes very obvious that they are not visible object lines. Whenever possible, avoid sending extension lines to an object like this. Okay, unless we absolutely have to. Okay, move this 0.5 over this side, move these two up here. Like that. General circle is dimensioned by its diameter and arc by its radius. Okay, so there, this is a hole and that's diameter. This is a partial, that is a radius. Holes are located by their center lines, which may be extended and use extension lines. So we will dimension from here to here to the center line. We don't dimension to the edge of a hole. Okay. Holes should be located and sized in the view that shows the feature. Do not dimension this way because we are dimensioning here to a hidden object. Okay, better over here. Same with here. We do not dimension this here. We do not do the location here. Okay, so this is much better. Do not cross the dimension line with an extension line. Avoid crossing dimension with leader lines. Okay, so here, for example, we don't want this line going through the dimension line. Now, extension lines can cross each other, but we never want to cross a dimension line with an extension line. Okay, and if at all possible, we should not allow the leader line to go through that as well. Okay, so here's a much better, and you can see it's much easier to read. Leaders point toward the center of the feature, should not occur horizontally or vertically. Okay, a lot of people do this. Okay, make it straight across, straight down. No. Okay, should go here. Okay, and as long as we use the hole feature when we're creating a diameter, it will automatically point to the center. Dimension numbers should be centered between the arrowheads except when using stack dimension, and then the numbers should be staggered. Okay, you can see right here. These all go across here. It's very hard to read that. It's better to stagger them like this. Concentric circles are dimensioned in a longitudinal view whenever practical. Okay, again, these are cylinders. We do not put the diameter symbols on those. Okay, we dimension them here and then we stagger them. All right, that is it for dimensioning.